Alright gang, so in this video what I want to do is talk a little bit about weight and use this as a way to introduce the idea of quantitative force diagrams. So when we talk about quantitative, what we mean is we're adding numbers to this. In the past, the force diagrams that we've done have been qualitative, meaning we've just been drawing the forces. We've been drawing the arrows, we've been drawing the equivalency marks, and that's been about it. Now we're going to start attaching some numbers to that. So what we're going to do here is use that idea of weight. And when we talk about weight, we're talking about weight as a force, and using the equation of weight equaling mass times the acceleration due to gravity, and then using that to be able to calculate not just the weight, but also other forces that are happening in our force diagrams. So let's do a little review. We've talked a lot about why things move, and we've come to the conclusion that things only accelerate when there's unbalanced forces that are acting on them. If they're balanced, that means there's no acceleration. So that could be that it's just it's not moving at all, or that it's moving at a constant speed in a straight line. But regardless, that idea of balanced forces is going to help us out a lot today. Now, when we talk about weight, we know that that is the force that's acting on an object due to gravity pulling on it. So the way we get that is we take the object's mass in kilograms, and then we multiply it by g, which is the acceleration due to gravity. Here on Earth, acceleration due to gravity is 9.8 meters per second squared. And then when we get to units, a newton, that's how we measure the force, the pushes and pulls, that is equal to 1 kilogram meter per second squared. In other words, a newton is how much push or pull you need to apply to an object to get a 1 kilogram object to accelerate at 1 meter per second squared. So let's apply that. Here's the problem. I have a 5-year-old with no filter at all. This is Cruz. And the other day we had some pictures out, and they happened to be pictures of when my wife and I got married. And Cruz was looking at that, and he's like, "Mom, who's that man in the picture with you?" And it kind of made me a little bit worried, because that guy that was in our wedding picture was me, and he didn't recognize me. I was in a little better shape back then, so that kind of told me that I need to switch some things around. So what I need to do is a little bit less of the donuts and a little bit more of the working out. So what we're going to do today is figure out how to use weight in these force diagrams by making fun of me. So here's what we'll start out with. So let's say that I have my weight. I want to figure out my weight in newtons if I have a mass of 93 kilograms. Now, also remember, you should be able to go from pounds to kilograms. But in this case, we'll keep it easy. I have a mass of 93 kilograms. What's my weight in newtons? Well, you guys know that weight is force due to gravity. You know that the net force that's acting on an object is equal to its mass times the acceleration that it's undergoing. In this case, that is just F sub g, which is the force due to gravity. So the way we calculate that force, or weight, is by taking the mass in kilograms, multiplying it by the acceleration due to gravity. So on Earth, once again, gravity, or the acceleration due to gravity, is 9.8 meters per second. So if I wanted to find weight, I'd take 93 kilograms, multiply that by 9.8 meters per second, and that means that I have a weight right now of 910 newtons. So I got to find a way to fix that. So the very first thing you do is, if you ever do P90X, you know that you've got they have a lot of equipment and other things like that. And one of the things that you absolutely need is a chin-up bar. Okay, so I went out, I bought a chin-up bar so that I could embarrass myself as I try to do these chin-ups. So here's what I want to think about. Let's say that I'm trying to do a chin-up. And usually what happens is I sit there and I pull as hard as I can, and I might be able to get one or two out, but eventually I just sit there and I hang. So here's what I want you to tell me. What's the total tension in my arms as I hang helplessly from my pull-up bar? So let's kind of think about this. If I'm just hanging from my pull-up bar, I'm not really moving. So that's a constant. And if my motion is constant, then that means it's balanced, or I have balanced forces. And if I have balanced forces, then the forces up equal the forces going down. So what forces are acting on me? Well, as I'm sitting there hanging, I definitely feel my weight, okay, my force of gravity acting on me, pulling down. And in my arms, I'm feeling that tension from my weight pulling down. So the tension is going up. So let's try to figure out exactly what the tension is in my arms as I hang from that pull-up bar. So we know that going down, we have the force due to gravity acting on me by the earth. And we figured out previously that I have a weight of 910 newtons. So if the other force that's acting on me is tension, and that's going up, and the forces are balanced, then that means that tension is pointed up also at 910 degrees. So those are equivalent. Now there's some of you that might be saying, Mr. Spencer, that doesn't make sense. You're not doing one-armed pull-ups. Okay, and that's true, because what happens if we think about this in terms of, instead of just total tension, as in terms of just both arms? Well, in that case, I still have a weight of 910 newtons. But if I'm hanging by two arms, that's a whole lot easier than just hanging by one arm. And the reason why is because each of my arms is taking half of that force. So in reality, what we have are two tension forces going up, each with 455 newtons, one for each arm. Now, the other thing that I'm trying to do is work on my box jumps, and what I have found is that while the guy on the left, okay, that's how you're supposed to do it, that's how in my mind I think I should be doing it, usually what happens with box jumps is embarrassment and blood and messed up shins. So let's use the idea of box jumps for our next one. So what I want you to do is draw a force diagram of the box with me on top of it. It was a very short box, and I was able to get myself up onto the box. So let's kind of think about what forces are acting on this box with me standing on top of it. Well, first of all, we have the weight of the box. Okay, so that's going down. We also have me on top of the box. So I'm applying that force to it. There's a downward force that's acting on it because I'm standing on that. But also the force that's supporting that is from the ground. So we have our newtons that are newtons. We have our normal force that's pushing up on the box from the ground to balance all of those out. Well, if that's the case, what are we going to do here to kind of figure out what the normal force is? So let's say that we know that the box weighs 150 newtons. And we want to figure out what's the normal force acting on the box by the floor with me standing on it. Well, once again, we have the gravity or the weight of the box. Okay, that's going down, and we know that this is 150 newtons. We also have my applied force pushing down, which is 910 newtons, which means that the support force of the ground is going to need to push up an equal amount to offset all of those downward forces. So in this case, the normal force would be 150 newtons plus the 910 newtons from me to add those up to get 1,060 newtons. All right, so that was pretty fast. So here's what I want you to be able to do. I want you to take what we've talked about, take what you know, and be able to show me how to solve these two problems. So here's what we've got. We've got a 180-pound Western high school football player, and he can deadlift 300 pounds. Now remember, 1 kilogram equals 2.2 pounds. I want you to do two things. First of all, I want you to use a force diagram to calculate the tension in each arm in newtons, just as he's standing there. And I also want you to calculate the normal force in newtons that are acting on the football player by the floor. So hopefully this makes sense. If you have any questions, just let me know.